So today and the next couple days, we're going to find what's called the line of best fit, and we're going to do this currently by hand. We're going to do it by hand. So this is going to go back to Algebra 1. It's going to go back to Algebra 2 to find a trend line or a line of best fit. Then we're also going to do something called using the sum of the squares of the residuals as a measure of that fit. So let's take a few quick review things here. A linear function. A linear function is any set of points that satisfy something like y equals mx plus b. And remember that m and b are constants. So they're not variables. And we also recall what m and b mean. So m is going to be my slope and b is going to be my y-intercept. So that's a function. That's a function. And it's a specific line, and because, of course, we're talking about a linear function, the result is a perfect line that goes forever into two directions. A linear model is this. A linear model is this. It's an abstraction. An abstraction that describes the trend of data. So an exact model would look something like this. So on a graph, if you have an x and a y, and let's say, for example, I'm just throwing in, for example here, let's say the number of shirts, and here you have the cost of, like the total cost. So if you buy 0 shirts, it costs $0. You buy 1 shirt, it costs $6. You buy 2 shirts, that's $12. 3 shirts, that's $18. I'm just saying that. All right, so notice here that it forms a perfect line because they're collinear. So in this case, it's called an exact model. All the data fits perfectly on the line that connects them. An almost exact model, we could talk about something like the number of hours studied and a particular grade or a GPA or something like that. So what you're going to see is that there will be different types of data. So some people who study 0 might do very poorly on the grade. So you're going to see data that kind of looks like this cloud, okay? Now, clearly you could have people that are going to be some people who study almost not at all and do very well, okay? You also have some people who study a lot and end up doing poorly, okay, for whatever reason. But generally speaking, we get this situation, and the trend line looks like that. Well, other times, impressionistic pretty much just means the kind of data is sort of all over the place, and yet it still has some sort of a basic trend. So you still see that the data goes up a little bit, but it's not a perfect situation. So it's impressionistic. It's more of where it's fuzzy. It's not a perfect correlation kind of thing. The first skill that we want to look at is we want to try to fit some data by eye. That means we're going to try to draw a line that crosses, it doesn't have to touch a single point. We're just trying to draw a line that kind of goes among the points that we think describes the trend, okay? So for example, since it starts high and kind of ends low, we might want to draw some sort of a line that goes somewhere like this. This one, clearly, we can draw something that goes in that direction, and the same with the other ones. We can make some sort of a line. So let's look at this first one here, and I'm just going to draw something that I think fits. Again, it's not, your fit is going to be slightly different than mine, but I definitely would not do this. I would not draw like this right here. Clearly, I wouldn't do that because we see that a bunch of the data is, there's some that's connected, but this one's kind of too far away, too sloppy maybe. So maybe I'll clean that up a little bit and just make it more like, whoops. And maybe that might not work. I'm just hypothesizing here. Again, look how far away this stuff is, far away, but these ones are close. So still, I might try it again and see what we get here. So bring it down a little bit. Okay, so maybe that works out a little bit better. So that's just by eye. This one here, we can quickly see. Here, the number in a set, and this is the numbers that are greater than the median. So let's just draw. Notice that this no point is actually being touched, except the one maybe up in the top there. So it kind of just goes right among all the data, but not necessarily touching any of the data. So the next ones are fairly straightforward. This one looks like it actually touches two of the points. And this one here is, I would argue, is almost perfect. Clearly not perfect, but almost perfect. So, all right. We're going to review now from some parts about finding the line once we've drawn the line by hand or the line is given to us, and try to actually find out what that line is. So first off, let's give some context here. This is the price of diamond rings that are sold in Singapore in a particular year. I don't know what year that is. Okay, but notice it's just an actual data. A 0.18, I believe, carats costs $702 in US dollars. Now down here, a 0.35 costs $16.29. All right, and as you see clearly, the data just increases. The larger the weight, the higher the weight, the more it costs, just like that. All right, so let's explain the steps real quick because most of us will need this review. So step number one is that you have to find the slope of the line. Well, actually, even better. We need to choose 2 points. Choose 2 points that are on the line. Number two, we want to find the slope. Number three, we want to use something called point slope form. You're going to substitute into that. And lastly, because generally speaking, our functions are going to be in slope intercept form. So number three is I'm going to use point slope form, and number five is I'm going to rewrite it into slope intercept form. So this requires us to have a lot of memory on things that we have forgotten. So the first thing, I need to choose two pretty kind of points that look on my point, on my line. So this one's sort of arbitrary because you have to go the best possible guess that you can. So I'm just looking along this line and seeing if I can find a decent enough point to choose. So I like to choose points that are kind of on the lines like this. Look, that one's at 1400 right there. So let me zoom in a little bit to see that. So my point here that I choose, this one right here, it looks like it is at 0.3. How do we count this? So that's a 1, 2, 3, 4. All right, so that's 0.32. 3.4, 3.6, 3.8, 4.0. So let me say 0.32, comma, it goes all the way up to 1400. So according to my trend line, I expect a diamond that weighs 0.32 carats to be $1,400. That's on the line. That's not actual data. That's just an expected thing. So I need to find another one. Oh, this one here looks pretty good right here, which is at, looks like 1.8 carats. Or sorry, try that again. 0.18 carats. And it goes all the way up to $600. So I've chosen 2 points, and those are them. We've chosen 2 points here, And now we have to substitute into the slope formula. Y'all recall the slope formula says this. M is equal to y2 minus y1. So the difference of my y's, also we call that the rise. And then x2 minus x1. And of course people ask, well, which one's the second point, which one's the first point? I ordered them up here, so this one comes first as I read it, and this one comes second. But it actually doesn't matter which way you go. I'm going to just go in the order here. So I start with the 1400 and subtract the 600. So 1400 minus 600 divided by, and then I go the 0.32 minus the 0.18. So by way of fraction, we get 800 divided by 0.14. And this will give me 5,714-ish. I'm going to say approximate right here. Why am I not going farther? How come I'm not using more decimals at all? Because there are decimals when we do this. Because let's see what this means. What does the slope of the line mean? It means that for every caret you go over, so this is not even half a caret right here, okay? But for every caret you go up, you have to go up nearly $6,000. So that's kind of like, this here tells me the approximate cost of 1 caret, okay? This is the approximate cost of 1 caret, the slope. So $6,000 a caret. Now that I have slope, I'm going to use point slope form, and many of us have forgotten what that is, so let's go ahead and recall what that one is. It looks like this. Y minus y1 equals m times x minus x1. So of course the question is, well, which one is going to be my, what do I put in for y and for x? Excuse me, the y1 and the x1. We're not going to put anything in for the x and the y, because these are my variables. These are specific points. That's a specific point, and that's a specific slope. So we're going to substitute here, here, and here, but not in for the x and for the y. It doesn't matter which point you choose. I'm going to choose this one because the numbers are slightly smaller. All right, so let's plug stuff in. We say y minus my y, which is a 600, equals, bring down my slope, which is 5,714, and x minus the x that's up there, 0.18. We're going to put this in slope-intercept form, which means I need to get y by itself. So I'm going to distribute this out first. Then I'm going to add the 600 to both sides. I distributed. Again, why am I not dealing with the cents here? Because cents on the thousands of dollars is not a very important or significant necessarily. All right, so now I just need to add the 600 to both sides to get my final result. Y is equal to 5,714x and minus 429. Again, because of the context, I chose to round things to not cents, because I'm not really using cents when I get to such large numbers. But you might find that the cents are being used. So just go with the whatever the context is. So let's interpret the line in the context of the problem. Interpret the line in the context of the problem. So what does this equation mean? What does it mean? And the key thing is, like we said above there, is that the m, which is 5714, is if you go up 1 caret, is equal to $5,714 increase in price. It's kind of like your slope. Not I mean, kind of, it is your slope. But it's up 1 carat is meaning that you're increasing the price by $5,700. Practically speaking here, this negative, this B part, really doesn't have much context very well, because ideally, because that doesn't make sense, because the negative 400 would be down here. And you ask yourself, well, what if I bought a diamond ring that had no diamond, right? That's what a 0 here would be. You would say, well, they would pay me $429. So practically speaking, having a negative cost doesn't really make sense, because that would mean the customer was being paid. So this one right here doesn't really have a direct, it's just sort of a shifter, a way to say that the cheapest ring you can buy is somewhere over here. Practically, we're not going to go into the negatives. So we can disregard this one. The most important part is the rate of change is 5714-ish. Okay. So let's talk about prediction as well. So why is this model not good for predicting the cost of a super, super small 0.05 carat diamond ring? Oh, I was spelling carat wrong. Sorry. C-A-R-A-T. Let's just practice it. Let's just try. So let me see. What if I went ahead and take the 0.5 and substitute in right there and see what we get? 0.05. So what would the cost of the ring be when we evaluate it at 0.05 here? So y would be, I'm just going to shove that into my calculator. So clearly, if I got a very, very small diamond ring, they would pay me to walk away with it. So clearly it's not a good model for everything. But it is a decent model. It is a pretty decent model for the data that we have. So in other words, if I wanted to predict not beyond, but I wanted to predict somewhere inside, like how much would be the 0.14 carat, or how much would be the 0.32 carat, or the 0.28 carat. So this would give me good information for the stuff inside the data, but not necessarily stuff outside the data. So let's answer this last question. Why is the set of data not a function? Well, if we recall what a function means, right? A function means that for every unique number, a 0.18, I should always get the same number here, the 702. So is there anything that repeats in the domain here? And the answer is yes. I do see this right here, right? The 0.18 repeats. And look, one seller was selling the ring for $664.50, and this one was $702. So that right there is why it's not a function, because this value gives me two separate costs. Another way to look at it, of course, is on the graph. You see right here, for example, these two, the vertical line test, it fails the vertical line test here, fails it here, fails the vertical line test there. So there are two ways that you can answer that question as to explain why. Number one, you could say that the data in the domain doesn't always go to the same data in the range. This being an example, 0.18 goes to two separate. Or you could say it fails the vertical line test in a few places. All right, so let's take a gander at what models are good for. What models are good for. So there are two special words. One is called interpolation, and the other is called extrapolation. So let this be helpful. The inter means inside, and the extra means outside. So interpolation, if you have a bunch of data on some sort of a graph, and this is my data, and then I have a trend line that is describing the data like this. Interpolation Interpolation is anything that's happening inside the domain given to me. So this kind of stuff would be interpolation. Because I'm making a prediction about what this missing link is, the missing data inside the cloud of data. So our example up here would be if I wanted to figure out how much 0.32 of a carat would be, and I interpolate that it's $1,400. And look, that fits fairly well with all the data. The next part is extrapolation. And extrapolation is data that's happening outside. So anything that's happening outside the domain. So if you're trying to predict what's going to happen, what it would cost a while ago, or what 2 or 3 or 4 carats are going to cost, way up here, that would be extrapolation. Extrapolation would be using outside the domain given to us. So just to review the steps here, what we did, number 1, we found the slope from this data, subtracting the y's over the subtraction of the x's to find this slope. Substitute one of the points, and it doesn't matter which one, into y minus y1 equals slope times x minus x1. Distribute out, and then I have slope-intercept form right here. To interpret, this slope means that the winning time will decrease by 0.01 or 1/100th of a second each year. There is no practical interpretation of this because this goes back to 1 BC. That would be the winning time in 1 BC. What I can do is, once I enter in that function on step number 3 above into y1 in my calculator, all I have to do is enter in y1 parentheses 2012 and do the same thing over here with 2016, and it'll yield me those 2 results. Next part. We use standard deviation to measure how good my point is relative to the normal. So we can also do that with 2 pieces of data. So we're going to measure how well a line models the data. So with just data, where we had just one data, instead of having like one category of data, the heights of people, for example, what we did is that we calculated deviation by subtracting the point from the mean. Then we found the average of the sum of the squares, and we called that the variance. Then from there, we did standard deviation. We took the square roots, okay? We're not going to go as far in order to use a number. So similarly, relative to the line of best fit or whatever trend line we have, whether it's the best one or not, we can see how well the observed data, the stuff that's actual, compares to the expected data, my trend line. So we're going to calculate, instead of calling it deviation, it's going to be called residuals. Okay? So what we do is the same as up here. We subtract the actual by the predicted. So the predicted is going to be from my trend line. And just like up here, we subtracted the mean. Then what we're going to do is just sum the squares, and then we're done. Okay, so we're not going to take the average, and we're not going to go further and take the square root like we did with standard deviation. So let's do step by step here what we expect. And we're going to calculate, first off, the residual. So we have a given line for us, okay? So 2,400 x plus 100, and this is 400 relative to diamond rings, prices of diamond rings, okay? So we're going to see how well this one fits. So we've got some data. Here's the actual data. So we're going to calculate what the predicted is based on the weight of 0.15 carats. We're going to substitute that in, see what we get. Then we have to subtract these 2, and then we're going to square it. So when I plug this into my calculator, 0.15 into here, I end up getting $760. The predicted is $760. based on, and this is the actual data here. So the residual of that is this. We say 484.5 minus the 760. This is the only time I'm going to write that. Every other time I'm just going to actually do it. So I get negative 275.5. What does the negative tell me? The negative tells me that my price, the actual price, is underneath the predicted price. So the negative says that this is the actual is under the predicted. Now we're just going to take a moment to square that. Good. So then we get 75,000. So keep going with this, where we are going to plug this 0.16 into your calculator, find the residual, and take a moment to square it. So now that my table is complete here, we see that some of my points are below, hence the negative. It's below my expected, the predicted based on the trend line, and a few of them are above. So I'm going to add up all of these and place my result there. So all of these add up to a rather large number, 237,778.75. So just to define what it is, we'll also tell you what it does. Okay, so the sum of the squared residuals is this, of course, 1 to however many terms we have, and we're going to do the observed, the actual data, minus the predicted. This is based on the trend line, which there are lots of different trend lines depending on how you have done it. We square those and we add them all up. Now, so here's the quick interpretation. Okay, so the closer the sum is to 0, the better fit of the data. Larger means that the data is more varied from the trend line. Not necessarily the line of best fit. And by the way, I don't even want to say the trend, beware of the word line, because it doesn't always have to be a line. So the trend graph. What we're going to see later is that sometimes my data isn't a line. Like for example, this. Notice that it's starting to curve. So if I were to describe this data, I might do a nice little curve like this, okay? And the sum of the squares of the residual actually helps me to tell, well, how close is this, how varied is the data relative to this curve? Or what if I was trying to fit my data into like an absolute value situation, right? Oh, look, my data fits pretty good like this, so how varied is it from an absolute value function or whatever other function we're dealing with? So let's take a gander at these two linear models to show you how the sum of the squares correlates here. So we have linear model 1. Squares are shown for a line that does not go through any data points. So notice this blue here does not cross through any single data point. So like we said, when you are drawing the trend line going through, it doesn't have to touch a single point. It might touch points, but it doesn't have to. This one over here, it does go through, it looks like some data points, or close to the case. So it looks like it's passing almost through this point here and almost through this point here. So let's see here. If we were to, remember that first off, the residual is this vertical line here. The vertical from the point to the line. Vertical point to the line. It's not the distance to the line, it's the vertical to the line. And then making a little square kind of gives you, first off, it positivizes all the values. And second, it also makes the values that are farther away, it makes it even bigger. It gives them more weight. So as you can see here, the squares are all pretty small here, and the sum of the squares is 59,000, and this one here is 237,000. So as we see here, because this one has a much smaller sum than this one, we know that this happens to be a better fit. Not necessarily the best fit, but better compared to the two. So that's a visual way of looking at sum of the squared residuals, or the sum of the square of the residuals. So we can speed this up by putting this information into L1 and L2, and then we're going to put this into Y1, and then our residual, we're going to have to do some massive fun calculation, and it's going to look something like this, where I say Y1 parentheses L1, and I'm going to subtract from, so my subtraction has to be on the other side, L2. 186. Now that we have the sum of the squares of the residuals here, we can compare it to the other one, which is, so clearly we see this one has a lower sum of the squares, or they also call it sum of the squared residuals. So which of the two models best describes the data? That's the one we're working at. So y equals negative 0.167x plus 13, because it has a lower sum of squared residuals.